Good?
Yes, we can see your
Okay,
slides.
good. Okay, so today I'd like to talk about some work that's being undertaken in my group into looking at how nanophotonics could contribute to new ways of processing images with a particular focus on phase contrast imaging. So when you think about image processing, you might think about, processing where the edges of an image are enhanced. This is actually very widely used in a huge range of applications, and it's generally performed these days using computers. But in fact, there's an enormous amount of information being generated, and the sort of systems that want to access that the results are actually becoming increasingly sophisticated. So there are actually concerns around, energy consumption and also the speed of processing. Furthermore, when you think about a conventional camera, it really only captures the intensity of an optical field. And there are and what that does, you actually discard phase. Now, there are well-known all-optical approaches for imaging transparent samples, such as the diatom shown here, as well as other live cells. But these methods tend to be fairly bulky. Some of the components are expensive. And this is in contrast to the current drive to miniaturize various devices and systems. So there actually remains an opportunity to develop new ultra-compact all-optical approaches to image processing that could also perform operations in real time. Now, when you think about enhanced images, these are some examples down here. And you can see that if the high spatial frequencies in the image are retained, that enhances the edges and highlights the fine detail in that image. On the other hand, if only the low spatial frequencies are retained, you end up with just information about the slowly varying background. Now, although images like these were generated digitally, well before computational approaches were widely available, all optical approaches were proposed and were quite widely used. So a typical all-optical system might look like this. You would have an input plane, the light, the image would pass through a lens, and you would end up in the Fourier plane here. So you'd have the Fourier transform of the input image here. You could then introduce what are referred to as spatial filters that would either selectively absorb or change the phase of the different spatial frequency components of the input image. Example here would be, for example, absorbing the low spatial frequencies. And then you would end up with an output image. And in this case, you'd end up with something that had enhanced edges. Now, this can be used to image phase objects because the Fourier transform in this plane is the full real optical field. And so if phase elements are introduced here, such as is the case with Zernike phase contrast, one can significantly enhance the intensity contrast of samples with relatively weak absorption. Now, systems like this, as I said, have been known about for a very long time, but they do tend to be relatively bulky. So if we want to create a device that's compatible with, miniaturized electronics, one would want to take all of this and reduce it to something that is of the order of a few hundred nanometers thick. Now, one proposal that's been put forward is to use graded index lenses and also take advantage of the properties of metasurfaces. And we've seen some nice presentations in this conference discussing them. And these metasurfaces could act as superior spatial filters. Another approach, and this is the one that we've been looking at, is whether one can design devices that have an inherent sensitivity to spatial frequency. And these can be placed in the object or the image plane within an optical system. So, for example, they could be incorporated into a cover slip that is adjacent to some cells, and the device itself would create contrast, intensity contrast. The device could also be directly integrated onto a camera chip. So let's take a minute to have a look at what is actually happening in terms of imaging in the spatial frequency domain. So this is in Fourier space. And if we want to describe the behavior of an optical system in Fourier space, we describe it in terms of the optical transfer function, which is a function of spatial frequency. Now, we would have an input field, and you would take its Fourier transform, and the output field would have a Fourier transform that is related to the input just by multiplying it by the input transfer function. Now, I should say in a system which is scalar, this function here is a scalar function, but when one is looking at systems where polarization is important, and in fact, a lot of the devices that we're looking at do actually fall into this category, the transfer function is actually a tensor. So once you have that output field, you can inverse Fourier transform that to actually find the field as a function of spatial position and also then the intensity. So if one wants to actually design a device that has a particular transfer function, it would have to be a device that has a particular sensitivity to angle of incidence, because there is this correspondence between angle of incidence and spatial frequency. So if we can do this, then if we can create devices like this, then we can perform this so-called object plane Fourier filtering without actually having to access the Fourier plane. Now, if you think about your favorite wave system, I'm sure everyone can think of materials and objects that have an inherent angular sensitivity. And that's certainly the case with optics. And there have been, over the last few years, this idea has attracted an enormous amount of attention. And so different systems have been explored, and these include, for example, thin films. And for example, thin films of metal where the excitation of surface plasmons is highly sensitive to angle of excitation. And this was used to generate edge-enhanced images of both amplitude and phase objects. We've also looked at metasurface type structures with exciting symmetric modes on these nanoparticle ensembles to demonstrate some edge detection, and also grating structures as well. So there are actually an enormous range of systems that can potentially do this. Now we're focusing on trying to generate nice phase contrast images, and I just want to talk about a couple of devices that we've been exploring over the last couple of years. Now, the first of this, they both incorporate waveguiding layers, and the first actually has a waveguide layer, and on top of that there is either a grating or some sort of metallic patch array. Now, this is a what's called a resonant waveguide grating, and it is a system that is highly sensitive to angle of incidence. And if we look at devices that were fabricated by Lucas Weizmann, who worked on this as part of his PhD, if we look at these Fourier plane images when we've got no object in there, we're just looking at what happens to focus light. And these are effectively related to the transfer functions. And for the different structures that were fabricated, one could see that at characteristic resonant wavelengths, we end up with a transfer function where low spatial frequencies, so those around normal incidence, are strongly suppressed. But as the angle of incidence is changed, as the spatial frequency is changed, the transmission through the device increases. If you go off resonance, the transfer functions look quite different. So the first phase variation we looked at was one generated by a spatial light modulator. So it's kind of a faux red blood cell type phase distribution. And we use the one-dimensional grating. So illumination from the spatial light modulator passed through the grating, and we looked at the transmitted intensity. Now, if the plane of the grating was at 90 degrees to the optical axis of the system, we could see that we ended up with this edge-enhanced image being produced. This is like what's called a dark field image when the device is present. If we take the device out, as you would expect for a phase image, there's negligible contrast. Things, however, get really interesting when we actually slightly tilt the device with respect to the optical axis, and we start to generate what's referred to as a pseudo three-dimensional rendering of this particular phase distribution. And this is very reminiscent of the sorts of images that are produced using differential interference contrast microscopy, which is widely used in biological live cell imaging. And this is a little movie just showing what happens when we move the device into and out of the path, and the change in contrast is immediately apparent. We, in collaboration with Liz Hind, who's in my department, we looked at some unstained HeLa cells. This is a differential interference contrast microscopy image of those cells, and we created the device on a cover slip, and not every section of the cover slip was actually patterned with the device. So in regions where there were cells but no device, you can see there was negligible useful contrast. However, in the regions where the device was present, you can see immediately the existence of this enhanced contrast. And it's interesting also to look at some of the finer features that are resolved by imaging with this device and comparing what we see with DIC and also a fluorescence image. So this particular device did involve introducing a tilt. Now that can be a little bit cumbersome in some devices, and also it's actually very interesting just to think about whether you can actually generate an asymmetric response in other ways, because by introducing a tilt, effectively what's happening is we're introducing an effective asymmetry into the transfer function. And such an asymmetric response is seen in systems where, and I'll say a little bit more about the mechanism here, but it was originally seen in the excitation of surface plasmons with a metallic film that was patterned with nanoholes like this. And when it was illuminated with right circularly polarized light, surface plasmons propagated to the right, and when the helicity was reversed, the surface plasmons traveled to the left. More recently, some theoretical work has shown that a device working on essentially the same principle, but now coupling light into a waveguide via excitation of nanorods, was also able to generate this asymmetric response. So the idea here is you've got two orthogonal rods. Note that with circularly polarized light, these are going to be excited 90 degrees out of phase with each other. They're also spatially offset. And what that does is it introduces another 90-degree phase shift in terms of the scattering into the waveguide. And in this work, it was shown that if you look at either the reflectance or the transmittance for both right and left circularly polarized light, what we see is an asymmetry in both the transmission and the reflection about normal incidence. And normal incidence corresponds to Kx equals 0 along here and along here. Furthermore, this asymmetry is reversed as you reverse the helicity of the incident light. So we decided to explore this device as for its potential for imaging phase objects. These are the parameters that we explored, and this is a finite element method simulation of the transmitted intensity. If we look at this particular feature here and plot the vertical component of the electric field and also the time average pointing vector, we can see that we're exciting waves in the waveguide to the left there. If we look at the rods, the surface charge on the rods, you can see that these are actually being excited out of phase with each other, which is exactly what you'd expect. If we reverse the helicity of the incident light, you can see that the light is propagating in the waveguide in the opposite direction. So this has this asymmetry, and that is further evidenced by looking at the modulation transfer function, which is effectively the square root of the transmission as a function of spatial frequency. Here you can see that although there's the response to the Y component of spatial frequencies is quite weak, you can see there is clearly this asymmetry in the X component, this horizontal component here. So again, we do have an inherently asymmetric transfer function. So if we simulate an input phase, again, our favorite little fake blood cell here, we would expect an output intensity that, again, has this particular rendering. So Lucas, again, fabricated this device. This is a scanning electron microscope of what was used. And this is the experimental, or the square root of the experimentally obtained transmission for both right and left circularly polarized light.
Sorry, it's 14 minutes.
Thank you. And these red lines are linear fits over this, this range of spatial frequencies. So an egg-crate type phase distribution was imaged onto the device, and you can see that in the absence of the this metasurface device, there is negligible or very weak contrast, which is significantly enhanced with the device present. Furthermore, the contrast is reversed when you flip from right to left circularly polarized light. Okay, so in conclusion, we've demonstrated object plane Fourier filtering of optical wave fields and applied it to imaging transparent samples and wave field phase variations. There's actually considerable potential for extending this approach using different structures that can be used to tailor more complicated transfer functions. And what this does is it presents an ultra-compact, all-optical, real-time solution for image processing with subsequent reductions in the power required to do this. And we also envisage applications in areas where space and weight are significant considerations. So I'd just like to conclude by thanking everyone who's contributed to this work, particularly Lucas Fazeman, who did most of the experimental work. I'd also like to thank sources of funding, and also the devices that have been fabricated were all produced at the Melbourne Centre for Nanofabrication. Thank you.
Thank you very much, Anne. Are there any questions from the audience? Well, maybe I can. Oh yes, Martin.